Hi. You've seen that the job of a programmer is to design processes that accomplish particular goals, such as finding the square roots of numbers or other sorts of things that you might want to do. We haven't introduced anything else yet. Of course, the way in which a programmer does this is by constructing spells, which are constructed out of procedures and expressions, and that these spells are somehow direct a process to accomplish the goal that was intended by the programmer. In order for the programmer to do this effectively, he has to understand the relationship between the particular things that he writes, these particular spells, and the behavior of the process that he's attempting to control. So what we're going to do in this lecture is attempt to establish that connection in as clear a way as possible. What we will particularly do is understand how particular patterns of procedures and expressions cause particular patterns of execution, particular behaviors from the processes. Let's get down to that. I'm going to start with a very simple program. This is a program to compute the sum of the squares of two numbers. I will define the sum of the squares of x and y to be the sum of the square of x, I'm going to write it that way, and the square of y, where the square of x is the product of x and x. Now, supposing I were to say something to this, like to the system after having defined these things, of the form the sum of the squares of 3 and 4. I am hoping that I will get out a 25, because the square of 3 is 9, the square of 4 is 16, and 25 is the sum of those. But how does that happen? If we're going to understand processes and how we control them, then we have to have a mapping from the mechanisms of this procedure into the way in which these processes behave. What we're going to have is a formal or semi-formal mechanical model whereby you understand how a machine could, in fact, in principle, do this. Whether or not the actual machine really does what I'm about to tell you is completely irrelevant at this moment. In fact, this is an engineering model. In the same way that an electrical resistor, we write down a model V equals IR, it's approximately true. It's not really true. If I put enough current through the resistor, it goes boom. So the voltage is not always proportional to the current. But for some purposes, the model is appropriate. In particular, the model we're going to describe now, which I call the substitution model, is the simplest model that we have for understanding how procedures work and how processes work, okay, how procedures yield processes. And that substitution model will be accurate for most of the things we'll be dealing with in the next few days. But eventually, it will become impossible to sustain the illusion that that's the way the machine works, and we'll go to other more specific and particular models that will show more detail. Okay, well, the first thing, of course, is we say, what are the things we have here? We have some cryptic symbols. And these cryptic symbols are made out of pieces. They're kinds of expressions. So let's write down here the kinds of expressions there are. And we have, so far, I see things like numbers. I see things like symbols like that. We have seen things before like lambda expressions, but they're not here. I'm going to leave them out. Lambda expressions. We'll worry about them later. Things like definitions. Things like conditionals. And finally, things like combinations. These kinds of expressions I'll worry about later. These are special forms. There are particular rules for each of these. I'm going to tell you how rules for doing the general case. How does one evaluate a combination? Because, in fact, over here, all I really have are combinations and some symbols and numbers. And the simple things like a number, well, it will evaluate to itself. In the model I will have for you, the symbols will disappear. Okay, they won't be there at the time when you need them, when you need to get at them. So the only thing I really have to explain to you is how do we evaluate combinations. Okay, let's see. So first I want to get first slide. Okay, here is the rule for evaluating an application. Okay, what we have is a rule that says to evaluate a combination there are three parts to the rule. The combination has several parts. It has operators and it has operands. The operator turns into a procedure. If we evaluate the operator, we will get a procedure. And you saw, for example, HAL type plus at the machine, and out came compound procedure something or other. Okay? And the operands produce arguments. Once we've gotten the operator evaluated to get a procedure and the arguments evaluated to get arguments, the operands evaluated to get arguments, we apply the procedure to the arguments by copying the body of the procedure, which is the expression that the procedure is defined in terms of. What is it supposed to do? Substituting the arguments supplied for the formal parameters of the procedure, okay, the formal parameters being the names defined by the declaration of the procedure. Then we evaluate the resulting new body, the body resulting from copying the old body with these substitutions made. It's a very simple rule. And we're going to do it very formally for a little while. Because for the next few lectures, what I want you to do is to say, if I don't understand something, be very mechanical and do this. So let's see. Let's consider a particular evaluation, the one we were talking about before. The sum of the squares of 3 and 4. Okay? Well, what does that mean? It says, I can find out what sum of squares is. It's some procedure. And I'm not going to worry about the representation of that. I'm not going to write it on the blackboard for you. And the 3 represents some number. But if I have to repeat that number, I can't tell you the number. The number itself is some abstract thing. There's a numeral which represents it, which I'll call 3. And I'll use that in my substitution. And 4, okay, is also a number. I'm going to substitute 3 for x and 4 for y in the body of this procedure that you see over here. Here's the body of the procedure. It corresponds to this combination, which is an addition. So what that reduces to, as a reduction step we call it, it's the sum of the square of 3 and the square of 4. Now, what's the next step I have to do here? I say, well, I have to evaluate this. According to my rule, which you just saw on that overhead or slide, okay, what we had was that we have to evaluate the operands, and here are the operands. Here's one, and here's the next operand. And we have to evaluate the procedure. The order doesn't matter. Okay, and then we're going to apply the procedure which is plus, and magically somehow that's going to produce the answer. Because I'm not going to tell you, I'm not going to open up plus and look inside of it. However, in order to evaluate the operands, let's pick some arbitrary order and do them. I'm going to go from right to left. Well, in order to evaluate this operand, I have to evaluate the parts of it by the same rule. And the parts are, I have to find out what square is. It's some procedure, which has a formal parameter x. And also, I have an operand, which is 4, okay, which I have to substitute for x in the body of square. So the next step is basically to say that this is the sum of the square of 3 and the product of 4 and 4. Of course, I could open up asterisk if I liked, well, the multiplication operation, but I'm not going to do that. I'm going to consider that primitive. So, and of course, at any level of detail, if you look inside this machine, you're going to find that there's multiple levels below that you don't know about. Okay? But one of the things we have to learn how to do is ignore details. The key to understanding complicated things is to know what not to look at. and what not to compute, and what not to think. So we're going to stop this one here and say, oh yes, this is the product of two things. Okay, we're going to do it now. So this is nothing more than the sum of square of 3 and 16. And now I have another thing I have to evaluate. But that's square of 3, well, it's the same thing. That's the sum of the product of 3 and 16, which is the sum of 9 and 16, which is 25. So now you see the basic method of doing substitution. And as I warn you that this is not a perfect description of what the computer does. But it's a good enough description for the reasons, for the problems that we're going to have in the next few lectures, that you should think about this religiously. And this is how the machine works for now. Later it will get more detailed. Okay? Now, of course, I made a specific choice of the order of evaluation here. There are other possibilities. If we go back to this, to the telestrator here, and look at the substitution rule, we see that I evaluated the operator to get the procedures, and I evaluate the operands to get the arguments first before I do the application. It's entirely possible, and there are alternate rules called normal order evaluation, whereby you can do the substitution of the expressions which are the operands for the formal parameters inside the body first. And you'll get also the same answer. But right now, for concreteness, and because this is the way our machine really does it, I'm going to give you this rule, which has a particular order. But that order is to some extent arbitrary too. In the long run, there are some reasons why you might pick one order or another, and we'll get to that later in this subject. Okay, well now, the only other thing I have to tell you about, just to understand what's going on, is let's look at the rule for conditionals. Conditionals are very simple, and I'd like to examine this. Okay, a conditional is something that has if, there's also cond, of course, but I'm going to give names to the parts of the expression. It's a predicate, which is a thing that is either true or false, and there's a consequent, which is the thing you do if the predicate is true, and there's an alternative, which is the thing you do if the predicate is false. It's important, by the way, to get names for the parts of things, or the parts of expressions. One of the things that every sorcerer will tell you is if you have the name of a spirit, you have power over it. So you have to learn these names so that we can discuss these things. Okay? So here we have a predicate, a consequent, and an alternative. And using such words, we see that an if expression, the problem is you evaluate the predicate expression. If that yields true, then you then go on to evaluate the consequent. Otherwise, you evaluate the alternative expression. Okay. So I'd like to illustrate that now in the context of a particular little program. I'm going to write down a program which we're going to see many times. This is the sum of x and y done by what's called piano arithmetic, which is all we're doing is incrementing and decrementing. Okay? And we're going to see this for a little bit. It's a very important program. If x equals 0, then the result is y. Otherwise, this is the sum of the decrement of x and the increment of y. We're going to look at this a lot more in the future. Let's look at the overhead. So here we have this procedure, and we're going to look at how we do the substitutions, the sequence of substitutions. Okay. Well, I'm going to try to add together 3 and 4. Well, using the first rule that I showed you, we substitute 3 for x and 4 for y in the body of this procedure. The body of the procedure is the thing that begins with if and finishes over here. So what we get is, of course, if 3 is 0, then the result is 4. Otherwise, it's the sum of the decrement of 3 and the increment of 4. But I'm not going to worry about these yet, because 3 is not 0. So the answer is not 4. Therefore, this if reduces to an evaluation of the expression, the sum of the decrement of 3 and the increment of 4. Continuing with my evaluation, the increment I presume to be primitive, and so I get a 5 there. Okay, and then the decrement is also primitive, and I get a 2. And so when I change the problem into a simpler problem, instead of adding 3 to 4, okay, then I'm adding 2 to 5. The reason why this is a simpler problem is because I'm counting down on x, and eventually then x will be 0. So much for the substitution rule. In general, I'm not going to write down intermediate steps when using substitutions having to do with ifs, because they just expand things too complicated. What we will be doing is saying, oh yes, the sum of 3 and 4 results in the sum of 2 and 5. It reduces to the sum of 2 and 5, which in fact reduces to the sum of 1 and 6, which reduces to the sum of 0 and 7 over here, which reduces to a 7. Okay? That's what we're going to be seeing. Are there any questions for the first segment yet? Yes?
You're using 1 plus and minus 1 plus. Are those primitive operations?
Yes. One of the things you're going to be seeing in this subject is I'm going to, without thinking about it, introduce more and more primitive operations. There's presumably some large library of primitive operations somewhere, okay, but it doesn't matter that they're primitive. There may be some manual that lists them all. If I tell you what they do, you should say, oh yes, I know what they do. So one of them is the decrementer, minus 1 plus, and the other operation is increment, which is 1 plus. Thank you. That's the end of the first segment.